Why not?
All right. Thanks for coming to this week's discussion hour. Today we have Erik Fredrickson, a PhD candidate at the University of Washington, and I'll let him take it away.
Hey, thanks, Naoma, and thanks everyone for having me. It would have been cool if I could be there in person, but I think the kind of Zoom remote era also presents a lot of opportunity to hear from different people from different places. So I'm excited to be here. Um, yeah, so today I'm going to be talking about primarily my results from a study I did out of the Cascadia subduction zone on seafloor pressure geodesy. Um, so I'll kind of summarize that work and then also show a bit of preliminary stuff I've been working on for a similar project out of Alaska. So this image has almost nothing to do with my talk other than I thought it nicely showed the two regions that we'll be talking about. Just in terms of kind of the formalities of this presentation, I'm totally happy to be interrupted. Just speak up. I have the chat window open, but I probably won't notice it. So if you want me to like stop and explain something, you can try to type in there, but I might not see it. Okay, of course I've got to get myself on the right screen. Great. So just a bit of an outline for this talk. Like I mentioned, it's going to start with a discussion of the Cascadia subduction zone and some seafloor pressure geodesy work I've done there. And then we'll talk about Alaska. And this kind of box in the upper right corner, depending on how you configure your Zoom, I've tried to keep stuff out of there. So if you're doing the view with my little picture in the box, put it in the upper right, and hopefully it won't obscure too much. So I wanted to talk about geodesy generally, just really briefly, and particularly geodesy on the seafloor and all the things we stand to learn through those kinds of endeavors. And there really are a lot of things that we can learn from doing geodesy work out in the ocean. In subduction zones, we can measure and quantify things like interseismic strain, transient fault slip and creep. I'm particularly interested in that one. Strain partitioning on the accretionary prism. In ridge transform systems, we can observe spreading rates, slip rates, look at volcanic deformation. I have a figure here from Bill Chadwick out of NOAA and the University of Oregon, and it's his inflation time series for axial seamount on the Juan de Fuca Ridge, which has been collecting data for many years now using seafloor pressure gauges. And then in terms of intraplate things, we can look at plate motions and rigidity and flexure. So on this figure here, I have what is probably now an outdated figure from Dave Chadwell showing some of his GPSA results showing the convergence rate of the Juan de Fuca plate in the Cascadia subduction zone. But if we start thinking in particular about seafloor pressure geodesy, I think it's a really interesting and compelling tool for studying questions about shallow subduction zone dynamics. So here we have a somewhat classical picture of a subduction zone with our continental overriding plate here and our subducting oceanic plate moving down and to the left. And of course, kind of one of the most important features of these systems is the megathrust, the seismogenic zone where megathrust earthquakes occur. And as we go deeper beneath that megathrust zone, we have some interesting phenomena such as slow slip earthquakes and tectonic tremor. And these are really well studied and quantified on land where you can place instruments above them and get some really fantastic high resolution readings. And I think seafloor pressure geodesy can essentially give us the same type of information out on the seafloor. So looking up dip of the megathrust, of the seismogenic zone, and looking for these transient slip and tremor processes. I guess for pressure, particularly slip processes on the offshore part of the subduction zone. And I think this is, a kind of a really important thing to do. And I grabbed these images this morning from the UNAPCO website. So we're just plotting up where GPS stations are located on land in Alaska and in Cascadia. And I just wanted to show these because I think they really emphasize, just how much data we're missing if we're not looking at the seafloor. Alaska has these nice islands that kind of help us extend out in the subduction zone, but even so, there's this broad region out to the trench where we just don't have any information, and there's certainly plenty of gaps where we're not collecting any kind of seismic or geodetic data. And then similarly in Cascadia, where we don't have the benefit of those islands, we're really just out in the dark for that segment of the subduction zone. And it's a really broad, large segment of the subduction zone. So if we want to really understand the entire process of subduction and how that works, we need to be taking measurements on the seafloor. And so digging in like a little more specifically than that, I'm really interested in these near trench slow slip and tremor processes and whether or not that may be happening, they may be happening in Cascadia. So here I have a couple examples from some relatively recent publications where these processes have been observed. So Ito et al. In their paper showed evidence for slow slip occurring just prior to the Tohoku-oki earthquake and the Japan Trench, which is the kind of the red box shown here. And similarly, Yamashita et al. Was able to document with an offshore seismometer deployment tremor processes happening near the trench, which is marked by this dashed line here. So occurring significantly offshore. And then finally, Wallace et al., using seafloor pressure gauges, was able to identify a slow slip earthquake and quantify the amount of slip that pretty much extended all the way out to the trench. So having seen these processes in other settings, I want to know, is this also happening in Cascadia? But Cascadia is a kind of tricky place to work, particularly if you don't have any measurements on the seafloor. And one of those reasons is because there's anomalously low seismicity on or near the megathrust. Here I have a figure from Stone et al. And the light gray dots show the historic seismicity kind of all around the Juan de Fuca plate. And then the black and red dots come from the 2011 to 2014 Cascadia Initiative Ocean Bottom Seismometer Experiment. And this is his catalog of those events. And the red events specifically are those that occurred on or near the subduction interface. And you can see it's really, a very limited data set, and most of the action near the subduction interface is happening at this really complicated triple junction where, there could be all kinds of things going on. So it's really hard to draw from seismic data in this region. Another kind of important factor is there's this large distance from the coastline to the trench, particularly in the northern end of the subduction zone. So trying to make observations offshore with a land-based network really isn't going to work here. And I think that's kind of demonstrated really well by this set of figures here. So these are models of locking from Schmalzli et al. For Cascadia. And I'm not going to go into too much detail here, but kind of the important features is that the red indicates highly locked, the yellow into white is more freely slipping. And both the model on the left and the model on the right were constructed and constrained using all of the available onshore data. And both of these models fit those data equally well, and yet you can see very clearly how different they are. And I think some of the important features are that, really close to the trench in the shallowest part of the subduction zone, we have, almost no constraint. This model having it fully locked, and this model having it, almost completely freely slipping in some locations. And then another important feature in my mind is the difference off Oregon here. Again, showing that there's very little constraint on the degree of locking there. So I think if we were to look for places where slow slip, earthquakes, or tremor might be happening offshore, this area off Oregon is a good place to look. But all of this kind of together to say that using only onshore data to try to understand what's going on offshore in Cascadia really isn't a workable solution. I'm realizing my outline here, I'm maybe getting a little bit ahead of myself, so I'm just going to skip past this. If we want to use seafloor pressure to try to understand something about subduction processes, I guess we first have to know, like, how does that even work? So if you have a pressure sensor on the seafloor, you can think of the pressure record that you collect as a sum of these various parts. So we have our base pressure, that's a function of the depth of the instrument. We have pressure from ocean and earth tides that are essentially just modulating the height of the water above your pressure gauge. We have this component of drift which is a function of these sensors that we use to measure the pressure and are generally characterized linearly. Then we have pressure from oceanographic effects that are non-tidal. And finally, we have geodetic pressure effects, so the kinds of things that I'm interested in detecting, such as displacement from a slow slip earthquake. And so if you're to look at a pressure record without altering it in any way, this is essentially what you'd see. And it's just totally dominated by the tidal effect and in some cases by the drift. And just to orient you, because I'm going to show a lot of plots like this, I almost always convert the pressure into equivalent centimeters of seawater. And that's because when I'm thinking about the deformation that might occur from slip on the subduction interface, I'm going to be thinking about that in terms of centimeters. So it's nice to be able to kind of have those units directly comparable. So as mentioned, the tidal effect is really big, but it's all right because that's really easy to take care of. We can actually eliminate kind of those first three terms by filtering for the tides and then detrending the data. So essentially subtracting out a linear term that'll get rid of that drift over the entire deployment period. And then I filter using essentially a bandpass filter because the kind of slip transients I'm interested in occur at timescales that are longer than the tidal component. But you can also use kind of any number of tidal modeling codes to achieve that. And so what I have here are a series of pressure time series that I've slipped in a synthetic slow slip earthquake transient into. And these have been tidally filtered and detrended. And what you'll see is that there's still a lot of residual signal that makes it very difficult to say where that slow slip earthquake displacement might be. And so we're really interested in getting rid of this oceanographic pressure effect. And there are several ways to do it, but one popular way is called station differencing. And what you do there is you assume that one of these pressure time series based on its location is one representative of the oceanography of the region. So your entire network of sensors is you're representing the oceanography of that area with this one reference sensor. And then two, it's not experiencing any tectonic deformation, so that you're not going to subtract out any of that kind of signal. And so generally speaking, the kind of typical technique has been to have a pressure sensor on the incoming plate where you know there's not going to be any deformation, and then run with the assumption that the oceanography captured by that sensor is representative of your entire network. So in this example, I'm using this central time series as the reference and then subtracting it from all the others. That's our differencing. And we have those resulting time series here on the right. And having done that, we've really effectively gotten rid of that oceanographic non-tidal pressure effect. And you can see much more clearly where I've slipped in that synthetic slow slip earthquake. So you can see the decrease that occurs in pressure over this kind of yellow banded period. Whereas if we look back here, it's really, you'd be hard pressed to see it. But the other thing I hope you'll notice is that this differencing, didn't kind of uniformly work uniformly well for each of these other pressure records. There's some where it really nicely gets rid of that oceanographic signal, and there's others where there's a lot of residual signal left. And if you were to see this pressure record on its own, you probably wouldn't be able to identify where the deformation had taken place. So this leads me to the kind of questions motivating this work. First, can these non-tidal oceanographic signals be effectively removed and consistently removed from the seafloor pressure data? And then having achieved that, what is the detectability of shallow slow slip earthquakes using seafloor pressure records? So in Cascadia, my data come from the Cascadia Initiative experiment that I mentioned before. This is predominantly a seismic experiment designed to characterize the seismicity of the entire Juan de Fuca plate. But some of the sensors had absolute pressure gauges, or what I'll call APGs, also equipped. And so the map here has a lot of information, but the symbols basically show you where those instruments were deployed. And kind of the important thing to know for the case of this study is that unfortunately those pressure gauges weren't left in the same location for the entire 4 years of the Cascadia initiative. So the different colors and shapes represent different years, and you can see that In the first year, we had instruments kind of to the north of the subduction zone. Second year, they were moved to the south. Third year back up north, and then fourth year back south. So we don't have a continuous record over this 4-year period, unfortunately. Also, I've kind of outlined these dotted areas offshore, and these represent regions where we have oceanographic, models of oceanographic circulation from physical oceanographers who kind of use the outputs to study how water is moving around this region. Predominantly used for things like, transport of heat, nutrients, et cetera. But they essentially contain the full 3-dimensional physics of the water in that region. So we can use that to calculate the bottom pressure and use these as kind of a model data set. So this is what the data from the absolute pressure gauges looks like once it's been tidally filtered and detrended. So getting rid of that tidal signal and that sensor drift. And I've color coded these by the location of the sensor relative to, I guess, kind of as a function of water depth. So the light green traces are on or near the shelf. The light blue are instruments on the slope. And then the dark blue are instruments on the abyssal plain. And this is just 1 year of data, just kind of to show as an example. And you can kind of notice right away in these time series that the amplitudes of these non-tidal oceanographic signals tend to be lower out on the abyssal plain and increase as you move towards shore. And this really, from an oceanographic perspective, makes sense because when you're in those shallower waters, surface effects are more readily felt on the bottom. Whereas once you get out to multiple thousands of meters depth, those surface effects don't always propagate all the way to the bottom. As mentioned, we also have data from these models of oceanographic circulation. And they're really nice in a number of ways. So if we look at this figure in the bottom left, in the blue, I have a time series from a APG sensor indicated by the star on this map. And the red trace, I have the same time series from the oceanographic model. And we can see that a lot of these peaks do match quite well, although the model tends to not always get the amplitudes right. And then there are certain periods where maybe it's not matching quite as well, particularly at maybe lower frequencies. And so what I show in this lower figure here is the difference between the model and the pressure gauge time series. And you can see that there's still a lot of residual signal in here. But kind of the takeaway from this is that these models do predict many of the signals that we see in the APG records. And because of that, they are a really useful tool to studying how bottom pressure kind of manifests and propagates on the seafloor. However, they're not sufficiently accurate to act as a correction. They're not going to be able to remove that kind of tidal or non-tidal component of the pressure for us. So they're really more of a tool for studying these oceanographic effects, but not a tool for correcting the data. And what I've shown, what this plot here shows is just the, if I take the time series at any point in the model and calculate its RMS in centimeters, I then just contoured that. So the blues are low RMS and the yellows are higher RMS. So we see a very similar picture to what we see from the APG data, that the signal amplitudes increase near the shore and decrease away from shore. So as mentioned, the kind of the standard technique for removing these non-tidal signals is differencing, and it's generally done with an instrument on the incoming plate. However, in this work, I was able to show that you can actually get a much better result in differencing by differencing along isobaths. So having multiple reference stations and only using those references to subtract out the oceanographic signal from instruments at similar depths. And so I try to show that here just as an example in this upper figure. We have a number of time series from different instruments that are listed in the legend here. And the first number is the separation from the uppermost time series. So we're looking at around 100-kilometer separation between these data. And then the second number shows their deployment depth. So looking at instruments around 120 to 150 meters depth. And just visually, you can see that these are very similar. And down below, I've performed the differencing, and you can see that, in fact, they are quite similar and eliminate a lot of that common signal. So the black trace here is our APG difference, taking this uppermost curve and this lowermost curve and calculating the difference. We go from something that was, an RMS of like 3 centimeters to something that's less than 1 centimeter. And what I show with these other curves are the equivalent difference using the model output, which shows a result that is largely in agreement with what we see from the data. And then finally, this is a difference if you first correct each of these time series with the model and then difference them, and just showing that, as mentioned, you really don't get anything useful by using the model as a correction. And so I could show a whole bunch of these different time series, but it would get pretty dull. So I've kind of just summarized, the broad results in this table here. Basically, if we set out to get differences that have a RMS amplitude of less than 1 centimeter, we can do so by kind of following these bounds on how we perform the differencing. So if we're looking at instruments deployed in really shallow waters, less than 100 meters, this technique really doesn't work. The oceanography is just way too variable. You're getting a lot of wave effects because you're so close to the shore and so shallow. They're going to create really noisy time series. However, as you go deeper, things start to work out really well. So between 100 and 250 meters, so long as the depth difference between your two sensors is 100 meters, they can be separated by as much as 100 kilometers. And when you subtract them from one another, you'll get a residual with an RMS of less than 1 centimeter. Similar story for instruments between 250 and 500 meters. And as you go deeper and deeper, essentially your tolerable difference in depth between the two instruments increases, as does their separation, and you can still achieve this 1 centimeter RMS result. And so when we're thinking about doing this in the context of identifying something like a slow slip earthquake transient, those offshore slow slip events in other settings have been found to have amplitudes maybe as high as 5 centimeters of uplift. But of course, that's going to be your peak uplift. As you kind of move away from that, it's going to get lower and lower. So if we can have time series with 1 centimeter or less RMS amplitudes, trying to identify a multi-centimeter slip signal, that's going to be really beneficial and really allow us to characterize that slip. And then another point that I kind of won't demonstrate with the plots, but you'll have to take my word for it. As you increase this, as you go beyond this kind of max allowable depth difference, the RMS increases really rapidly, and you have a really large residual oceanographic signal, so making it increasingly difficult to identify and quantify slip transients. And to go back to the oceanographic model, again, it's a really useful tool for studying kind of the regionality of this bottom pressure. So what I show in this figure here is we take the model output from the starred location, difference it against all other points in the model, and then contour the RMS. And so you see this effect really nicely that I just laid out using the APG data, that as you follow kind of a constant depth contour, you have really low residual RMS. But as you move away from that, it becomes increasingly large and more difficult to identify a tectonic signal. Yeah, and then I guess just to reiterate, if you're thinking here, I have roughly the trench contoured, and if you're thinking about having a reference station out here and differencing against kind of stations on the slope or continental shelf, it's really just not going to work well to reduce those oceanographic signals. Okay, so now hopefully this point in my outline, which I think I got to a little too quickly, makes sense. Using this what I call depth match differencing technique is really effective in reducing oceanographic noise. So now that we kind of have this technique in hand, we can start thinking about modeling what deformation might look like in Cascadia in order to determine the detectability of slow slip events in this setting. So in order to do that, I set up a series of elastic half-space models, and I'm just kind of demonstrating what one of those looks like here. So this kind of triangular gridded region is the Cascadia fault interface adapted from McCrory et al. And onto that, I've kind of colored each patch according to the amount of slip I've assigned it, according to this scale here. So this particular model has up to, I think it's 32 centimeters of slip. And then I essentially built these models to be Gaussian, both in kind of X and Y, so they taper off smoothly from that max slip. In particular, I was modeling off this region of Central Oregon, because as I mentioned, that would be kind of the most interesting place to try to go and look for slow slip earthquakes in Cascadia. And for those interested, the physical parameters I used for the model are in line with what you'd expect for the accretionary prism at Cascadia. And then, as I mentioned, this is just one particular model. It has a magnitude 6.4, has a stress drop of 0.06 megapascal. But this was essentially just our base model for this study, which we then increased and decreased the magnitude, changed the stress drop around, trying to get end members for all the different events we might expect. And so for evaluating the detectability of this and other such models, based on kind of the result we were able to achieve of getting differences with less than 1 centimeter RMS residual, we prescribed a 1.5 centimeter threshold for what we call unambiguous detection of a slow slip signal. And this is pretty conservative. It corresponds to a 2 sigma offset in our time series. So very clearly detectable signal. And so the way we kind of did these detectability tests is that I made 2 very simplistic station lines. One kind of in the traditional method of a reference station marked by the star on the incoming plate, and then a line of instruments that just goes on up the slope on the shelf towards shore. And then we had another line of instruments based off of my depth match differencing, with a reference station on one end and then stations that follow an isobath. And for each of these station locations, we used the oceanographic model to pull out a representative time series for that location. And then for any of these locations then these contours in red and blue, these represent the uplift in red, substance in blue of that base model I just showed. And in particular, this bolded region is our detectability threshold, so 15 millimeters, 1.5 centimeters. And so for each of these kind of modeled time series, we would then add in the deformation from this particular model over a period of 14 days. And again, that just comes from what's been observed elsewhere. We ran a number of different models from 7 days out to 30 days, but this one is 14 is most representative. So at the end of this, we essentially, for each station location, we have a time series with deformation added into it, over a period of 14 days, and then we can perform our differencing and see what we're able to detect. And so that's what I've shown here. This is our across strike line on the left and our constant depth line on the right. And so starting with the across strike line, which is kind of like the typical methodology, we move from furthest offshore on the bottom going towards shore as we go up. And I've just artificially offset these so you can see them all. So I've just taken away the mean and added an arbitrary number just to get them all visible. And as we move from our reference station up the slope, we get into the deformation, the uplift zone of the model deformation. And those time series marked in red are the ones that are above that 1.5 centimeter threshold. And so you can see that in this particular example, you certainly can pick out that uplift deformation, particularly on this trace where there's not a lot going on. You get that uplift and then not a lot going on afterwards. As you move further and further away, it becomes maybe more ambiguous, and you can imagine scenarios in which if you only had a few of these time series, it might be difficult to say where the deformation is occurring. Is it just here or is it this entire piece? So kind of one of the faults of this method kind of already starting to crop out. And then as we go into the subsidence region marked by blue, it becomes even more apparent that this method really isn't effective. You'd be very hard pressed to pick out the deformation signal in these time series. However, if we look at the constant depth line, in this case, we're going from our reference station in the south up north to the end of our network. And these differences, even across this entire large region, are really effectively removing that oceanographic signal. And so when we pass through the uplift lobe, any one of these time series, it makes it very clear where that deformation is occurring. And not only that, you can quantify the amount of that deformation. So if we're thinking real world scenarios, actually observing a slow slip earthquake, you're going to be able to take this information and get a much more accurate model of what the earthquake looked like from these data. And then to show just like another example, this is kind of our low end magnitude model. So going from a 6.4 to a 5.9, and you can see the surface deformation contoured here. So again, that bold red line is our 1.5 centimeter uplift zone. And for the subsidence, we don't even achieve that amount. So a much smaller event. I've also contoured the 1 centimeter uplift and subsidence contours just for reference. And so similarly, we look at the across strike line, and you get into this region where you're in that 1.5 centimeter uplift, but you'd be totally hopeless trying to identify that signal. On the other hand, using depth match differencing in this line of instruments along an isobath, you can very clearly see that signal. And you can even see, beyond kind of the 1.5 centimeter threshold that we set for ourselves. So kind of taking all this and our other models put together, we proposed an idealized network for detecting slow slip earthquakes off Oregon in Cascadia. And that's what we have here. So each of these triangles is just a theoretical station location. And these have been deployed along isobaths in several lines so that you essentially have your pick of reference instruments on any of these lines. And it's kind of suitable for capturing a slip, whether it occurs more up dip or more down dip. And so here I've also included that 1.5 centimeter uplift and subsidence from the base model, just to kind of give you a sense of scale. And this network's really designed at aiming an event of this size or larger reliably, no matter where it occurs. I'm also just quickly throwing on the smaller event here to show that that decrease in kind of the footprint of the deformation really makes a big difference. So having a smaller slow slip event, you could theoretically detect it on a station, but the odds are much lower that the deformation will occur in a location where you have an instrument. So that becomes kind of a limiting problem there. The other component that I kind of forgot to talk about in the previous slides is that based on the amount of slip in these models and the local convergence rate in this setting, we're looking at kind of recurrence intervals of events like this on the order of 5 years to 10 years at best. So the other component to setting up a network like this is that it really has to be a decadal scale effort if you want to be able to capture a slow slip event if they're occurring. And it's a complicated problem because from the shoreline, we have limited ability to tell when these are happening or where they might be happening. So it's a bit of a shot in the dark, and it requires a time commitment on the ground to hopefully be able to identify things like this. So just to come back to these motivating questions, we showed that this depth match differencing is really effective at reducing the non-tidal oceanographic noise, going from RMS amplitudes of greater than 3 centimeters down to better than 1 centimeter. So really improving our ability to detect deformation on the seafloor. And just a reminder that oceanographic models are really useful tools for studying kind of the physics, the ocean physics that generate these bottom pressures, but they're not useful as a correction because they're just not sufficiently accurate. And in terms of the detectability of slow slip earthquakes, there are kind of any number of magnitude 5.9 or larger scenarios that produce detectable deformation, or I should say resolvable deformation, but really we're talking about magnitude 6.4 and larger that would realistically be detectable with a modest network. And that's kind of the scale that's comparable to what's been seen elsewhere. Other places have reported these earthquakes on the order of magnitude 6.5 to 7, and that's also consistent with the kind of slow slip earthquakes we see in the down dip segments of subduction zones. All right, so now we can move into talking a bit about Alaska and just kind of the preliminary results of applying what was found in Cascadia to this setting. So I just want to orient everyone kind of with this geologic setting and the seismic history. So I have a map here from Lee and Freimuller that shows kind of the Alaska Peninsula area. These contours show historic large megathrust earthquakes, and then these kind of different segments of the subduction zone are labeled, and these are kind of determined based on their seismic history. So we have the Sanak segment, what we call the Shumagan Gap, where there hasn't been a large megathrust earthquake in recorded history, the Semity segment, and then the Kodiak segment. And on top of this, I've also overlaid this kind of translucent yellow oval, which unfortunately looks like it got moved, so it doesn't belong here. It should be more down this way, and that was meant to represent the location of the recent earthquake that we actually had in the Shumagan Gap. So in July, there was a magnitude, I believe 7.8 earthquake in this region. And then just a couple of weeks ago, there were aftershocks here. And from the same paper, I wanted to show the locking model that they determined for this setting. And this should be taken with a grain of salt because, again, there is that issue that this model is predominantly produced from instruments that are kind of onshore, away from the updip segment of the subduction zone. So we have some instruments on islands here. The kind of purple arrows show their kind of modeled residual for producing this locking model, but most of it is coming from the peninsula itself. But there are just kind of broadly important features. Again, red is highly locked. In this case, blue is less locked. And there does seem to be a good constraint on high locking kind of off in the shallowest part off Kodiak, and that becomes increasingly less locked as you move to the west. So here I've plotted instruments from the Alaska Amphibious Community Seismic Experiment. So this was another ocean bottom seismometer experiment that also had some pressure gauges equipped. So in this case, the instruments were deployed in kind of early summer of 2018 and collected at the end of the summer in 2019. So we have about 14 months of data. And kind of the different symbols here show where there kind of should have been data recovered and where there was actually data recovered. So kind of the important point is that the infilled black triangles are where we successfully recovered seafloor pressure data in this setting. And so these are what those time series look like. And in this case, these are just organized from the deepest instrument at the bottom to the shallowest at the top. Again, we have our pressure in centimeters, and I've just artificially offset these so that they're all easy to see. And just looking at this, kind of broadly in this kind of view, again, we see that, the kind of the amplitudes of these non-tidal signals are much lower for our deeper instruments and quickly become much larger at the shallow locations. And in this particular case, it's also quite obvious that there's a seasonal component to the signal amplitude, where when we get into our winter months, particularly in shallow locations, those amplitudes increase. And then in this setting, we also have a physical oceanographic circulation model that we can use to study these pressure effects. So in this plot, I've contoured the RMS amplitudes of the tidally filtered APG data out of Alaska, and we see trends that are similar to what we saw in Cascadia. Generally, we have low amplitudes at depth, and these become increasingly large as you move towards the shoreline. And the model shows a similar picture, kind of down to about 4,500 meters, and we have these generally low bottom pressure amplitudes that rapidly increase as you move on the shelf. And then one of the kind of interesting features in Alaska is that those signal amplitudes then start to increase again as you move out onto the abyssal plain. So it's clearly a more complicated oceanographic situation at depth here in Alaska than it was in Cascadia. And the other important feature to think about or to notice is that the amplitudes predicted by the oceanographic model generally tend to be lower than those that we observe in the pressure gauge data. And so I've just quickly overlain the pressure gauge contours here, and you can kind of generally see the similar kind of linearity of features along isobaths. But again, those amplitudes are different. And I guess another caveat with the model, at least for right now, is that we only have the model for the year 2018. And we don't have any 2019 model output yet. So we can only kind of compare half of the APG deployment to oceanographic model output. But even so, we see kind of similar features as we saw in Cascadia, where for shallow instruments, here we have an instrument at about 150 meters depth. The pressure gauge in blue and the model in red generally seem to agree on a lot of like the timing of various peaks, but not necessarily on the amplitude. And then, but there are sometimes where they get off from one another. So again, here plotted as the residual between them, and it's capturing something about the oceanography, but not enough so to be able to be used as a correction. And in this case, things get much worse as you move into deep water, where the pressure gauge in blue is very different from what we see predicted by the model in red. So again, a more complicated situation in Alaska at depth, not only for kind of this, that also influences the oceanographic models. However, so far it looks like depth match differencing does work in Alaska. We're seeing similar trends, but generally higher noise floor. So we're not able to achieve as low an RMS in these signals as we did in Cascadia. So here I have two instruments that are deployed at about 3,500 to 4,500 meters depth. And visually you can see they're very similar. And when we difference them, we very effectively remove that oceanographic signal. These are instruments kind of more up on the continental slope at 1,800 meters or so, and same kind of effect. And then we move into shallower water here at like 150 meters. And you difference them and you are getting a better signal, but that RMS is just much higher. So it seems like the trends identified in Cascadia are holding here, except that the kind of minimum achievable RMS just seems to be higher in Alaska. And we can look at the model in the same way to try to understand the regionality of how this differencing works and when it doesn't work. So here we have kind of a deep example, a slope example, and then a shelf example. And they're all essentially the same, where again, the starred location is where we extract a reference time series, subtract it from all other locations in the grid, and then contour an RMS. And so we can see the deep water situation is complicated, where it's not all uniform like it was in Cascadia. However, when we get on the continental slope, we see this kind of linearity of features that follows contours of constant depth, and gives us a nice low RMS result. And then when we get on the shelf, things start to get a little complicated, where there is some kind of commonality of the signals at this depth, but it's much more narrowly constrained. So another kind of interesting thing to think about and study, and that I'm trying to put some work into, is that in this particular setting, we actually have over a decade of output from this oceanographic model. So we can look at how seafloor pressures evolve, not only over the period of our instrument deployment, but also, interannually over these really long time scales. And I think one thing that's very clear from Alaska is that oceanography is really, it's a big obstacle in obtaining high resolution measurements on the seafloor. We have this kind of really complicated oceanography in this setting that makes it hard to get the most out of our geodetic data. So I think one thing that can be achieved with these models is really understanding what are the kind of oceanographic processes that are causing these residual signals, and why are they so variable from one place to another at the same depth as compared to Cascadia. And so this movie that's been playing is just the bottom pressure for the 2018 year, contoured based on RMS. Or I should say it's bottom pressure anomaly. And we can see, this kind of really complicated oceanography at depth in Alaska. We have these eddy-like features that propagate through here. We have a very large circulation feature, offshore. So this is what we're seeing in the model is consistent with what we're seeing in the data, that complex oceanography at depth in Alaska, it is an issue it makes it, sorry, I should say it makes it difficult to remove those signals from the pressure gauge data. And I think this movie is particularly nice in thinking about if you were to kind of set up a traditional slow slip earthquake detection experiment here with a reference station on the incoming plate, it would be hopeless. I mean, the oceanography here is nothing like the oceanography on the rest of the over the rest of the region. So in terms of future work, I mentioned kind of the interest in what processes are responsible for the residual signals and pressure differences. I think both in Alaska and Cascadia, what is causing, what is happening in the ocean that is causing these differences from one location to another? And is there anything we can do to kind of better characterize that or better correct for it? And then I think a related question is, why are these signals larger in Alaska across the board? I mentioned that at depth, the oceanography is really complicated in Alaska, but also up on the continental slope and on the shelf, Alaska seems to have these larger amplitudes than in Cascadia. Then also, kind of a big question is, can we improve these oceanographic models to make them more reliable for the sake of predicting bottom pressure? As mentioned, these models are generally used for studying how water moves around, moves things like heat, nutrients, et cetera. They're used by physical oceanographers to study physical oceanography. But an interesting question would be, could these models be tweaked or redesigned to more reliably predict bottom pressure? And what would they need to be able to do that? One obvious thing would be more data coming from deeper regions. One of the issues with these models is that they're largely constrained by things like tide gauges or measurements close to shore, because those measurements are easier to take. So they're kind of naturally biased to shallow waters. Thinking longer term for this work, really interested in merging offshore and land-based data sets. I think that's going to kind of be the key to the future, right? Is as mentioned, to kind of understand subduction zones, we really need that offshore component. But then, of course, we also need the onshore component. And so being able to do more studies that use both of those and do so effectively. And then the other component for me is really these long-term observations offshore. A lot of these processes, they're not happening in a given summer, over the period when we deploy these sensors sometimes. So having these multi-year experiments to be able to capture these phenomena, I think is really important. And then also coming up with more sophisticated methods to get the most information out of those data. All right, and with that, I'll conclude and take questions. Just want to kind of thank and acknowledge the various crews and scientists who produce these data sets. Of course, my advisor and committee, who in the COVID era have been really helpful. This is a picture of my general exam, which I had to do remotely because of the coronavirus. And then, of course, I have funding sources from NSF. Thanks.
All right, thanks, Eric. That was a great talk. So we'll go ahead and take questions for anyone who's got them.
I've got one.
We've got emoji and maps.
I've got one. So Eric, that was a great talk. First of all, I'm really curious about some of the assumptions or the data that goes into that oceanographic model. So like, how good does the bathymetry matter significantly to those models? And if so, how accurate is the bathymetry being used for the Gulf of Alaska case?
Yeah, so that's a really good question. The bathymetry is really important. And I think there's kind of like multiple things I can say about this. One thing that I'm really interested in looking at, and that I have an opportunity to look at in Cascadia, is the model used there was recently like revamped to include kind of higher resolution, more accurate bathymetry. So I think kind of doing a direct comparison there would be really interesting. In Alaska, I'm not as positive. I know a little bit less about that model, just having only started working with it more recently. And so I'm not as positive about kind of the quality of the bathymetry used in that model, or or when it was last updated. So I guess I can't maybe quite answer that. But I do
because
think
there was a big
yeah.
update in the bathymetry that occurred when the law of the sea work happened. And I just don't know if they used the bathymetry from before that. You know, that was almost a decade ago now. So you would think they would have it. But if they used the bathymetry before that, they missed whole seamount chains and things earlier, which would make a huge difference to your
absolutely
seafloor oceanographics. So I guess in a related question, how important is the stochastic on these pressures, like the big Aleutian lows that roll through every 4 days if you ever try to sail there in the winter, for instance?
Yeah, so I think, especially for like the kind of timescales I'm interested in, those are the effects that I'm kind of most interested in being able to eliminate from the records, because you know, they're kind of occurring at amplitudes and timescales that are comparable to what we might expect from a slow slip earthquake. So it's really hard to pull those apart. The other issue with them, as you mentioned, a lot of these effects are stochastic. So I'm particularly thinking about like these mesoscale eddies that roll through, these what are called coastal trapped waves that kind of come off the continental shelf. And so the models, as mentioned, you know, like the models are really useful tools because they contain all of those features, but the location and the timing, right, are not going to be just right. And I think it becomes a tricky problem, because even if you have, for instance, like we have now these seafloor pressure records from these settings, and you could envision assimilating those into these models, right, and creating, you know, tie points. But it becomes a problem because they're still really sparse, and the way, you know, these kind of assimilative models work is everything else will kind of deform to accommodate those data, right? So you can potentially capture that one eddy at the right time, but it's going to, you know, kind of have effects on the entire model field. And after the eddy passes, you know, it's the model's going to have it spin off one way when in reality it went another, right? So it's a very difficult problem, but it's something I'm interested in figuring out. Maybe we can't chip away at the entire thing, but other pieces that we can improve on.
Yeah. Thanks.
Awesome. Any other questions?
I had a question.
Sure.
Yeah, great talk. That was really interesting. I'm wondering if cables will play a big part in the future. I don't know if that's, I thought it kind of was going on in Japan, but maybe I'm wrong. But I'm wondering, like, if you kind of had cables that were going from near the shore way, you know, offshore from the shelf all the way towards the deformation front, if, you know, in your models, you might see some different results if you had a continuous stream of data, and maybe it would act more like a fiber optic cable where you could see that continuous movement along those lines.
Yeah, I totally agree. I think kind of cabled observations, both in terms of, you know, you can think of like the Japan model where they have these really nice networks of seismometers and pressure gauges over their subduction zones. And so you have, you know, not only high spatial resolution kind of sensor deployments, but you also have the data coming in at more or less real time. And that's huge. And then the other thing you kind of mentioned is like the possibilities that are opened up by kind of what's been shown with DAS recently, right? This, I always forget what the acronym stands for, but this kind of fiber optic interferometer stuff that you have the potential to, like, you know, really whether it's observing the kind of geodetic deformation or observing the oceanography, to be able to do so kind of in this really high resolution way, again, pretty much continuously with a fiber optic cable, I think is really powerful. So I think that really is the future. It's an expensive future, but I think it's a really important one. So I'm really interested in those kinds of systems and seeing what they have to offer.
Oh, awesome.
Excellent. Well, thanks so much for coming to visit us and give us a talk, Eric.
Yeah, thanks for inviting me.
Awesome. All right. I'll CC you on the email for the recording in case you.
Great.
All right.
All right. Thanks so much.
See you next week.
Thanks.